we wanted to talk and share a few ideas about machine learning with few labels. My name is Rahul Parandekar. I'm the founder of AI Hero. And Tobias, you want to introduce yourself real quick?
Yep. Hi, I'm Tobias. I'm a data scientist at Merck, Germany, and recently also like an ML consultant that you can hire. Roland.
I'm Roland. Been doing machine learning for quite a while now, and since last year, I'm an independent consultant, also available for hire. And today, we want to talk about a couple of new things in machine learning, which enable you to need much fewer labels than before. Things like zero-shot learning, few-shot learning, weakly supervised learning, zero-label models, and distillation. We'll start with zero-shot learning applied to text classification in this class. Zero-shot learning uses the fact that labels can have a semantic meaning. If you want to categorize news articles into sports, politics, entertainment, world news, all of these words have a meaning, and we humans use that if you want to do categorization. So let's try to do the same with our machine learning models. And it turns out that with recent large transformer models such as BERT or Roberta or Distelbert or many of the other models that have come out recently, we can frame this problem as a natural language inference problem. In natural language inference, we have two documents, one of which is a premise and the other is a hypothesis, and we try to predict if the two documents are related, if the premise entails the hypothesis, or if it contradicts it, or they're neutral, they have no relationship to each other. In this case, the premise is the document that we want to classify. The hypothesis is a synthetic phrase. This text is about whatever label we have. And we ask the model to do a natural language inference prediction about this. If the prediction is entailment, we label that text with that label. We do this for all labels. And then, depending on the setting, if you have only multi-class problem, then we'll choose the label that had the highest probability. If not, if we choose all the labels that are over a certain threshold. And surprisingly, this works quite well. On Yahoo Answers, which is a data set containing, 1.6 million documents, you can get the 37.9% F1 using a small BERT model, or up to 53.7% using a BART large model. Yahoo Answers has 10 classes, so a random baseline would obtain 10%. Compared to that, getting 53.7% is pretty good, especially considering that you don't have to do any labeling to get that. There are all kinds of variations on this, but they all use basically the same thing. From passing to the BERT model the documents, one of the sentences is the document that you want to classify. The other one is the hypothesis style. This document is about something. The nice thing about this is this can actually generalize, and you can use one model for multiple different tasks. Hugging Face is a very popular library that can be used to do zero-shot classification, and they offer a pipeline for this. And then in 5 lines of code, you can actually get started and start classifying documents without having to do any labeling at all. So the pros of this approach is that you have to write only 5 lines of code. These are 5 lines of code that are the same no matter what project you are working on, and coming up with the labels is the hardest part often. And you get pretty good results. And it can generalize to new labels and new tasks. The cons of this approach is that fine-tuning it is a bit tricky. The model is trying to do a natural language inference problem, so you won't be directly optimizing for improving the text classification accuracy. The other bigger con of this method is that it's inefficient for a larger number of labels. You have to run the BERT model once for each label that you have. So if you have 10 labels, you have to do 10 inferences with the BERT model. If you have 100 labels, you have to do 100 inferences. This can add up, and it can become quite costly quite quickly. I'll hand it over to Rahul.
Thanks, Roland. So zero-shot learning is also recently gaining traction in image categorization. So this example here shows what zero-shot learning for image classification is all about. As Roland mentioned, we exploit the semantic meaning of the labels when we're doing zero-shot classification. But along with that, what we can do is use the textual descriptions of images to train the model to understand what the semantic content of the images are about. And so you can see on the left, you use these images and let's say the classes that were assigned to them. You use the class descriptions using Wikipedia or some other sort of corpus you have to create a label space mapping, which assigns or which understands the semantic features in the image. And so during prediction time, as you see on the right-hand side, you have classes which are not necessarily names of birds in this case. They are more like descriptions about the bird. So blue plumage with brown wings, seabird with red eyes, small bird with mostly yellow plumage. These are your class labels. And so now that you have some semantic understanding of what that image is about, you can use zero-shot classification to match your image to whatever is the nearest embedding for these classes and give zero-shot classification. Next slide, please. And another interesting way to do this was proposed by OpenAI called contrastive language image pre-training. And so they use a contrastive method for training the models, basically pairing up documents and the labels for the documents. So on the left-hand side, you can see how this data set is created. For each image, you have an image encoder, which I1, I2, I3, ... IN are the N images you have in your data set. And text encoders are your regular bird kind of text encoders, which will give you something like text embeddings from T1, T2, ... TN. So you use I1, T1, which is the image and the text for one image as a positive label, and you use I1 and I2, ... IN as negative labels. So that's typically how you do contrastive learning. For example, for face recognition, you use the same contrastive technique over here, and you train the model. Once you have the model trained to use it, the candidate labels that you see on step 2, you create some sentence out of it, saying like a photo of a car, plane, dog, whatever, and you generate the text encoding for it. You use your image encoder head to generate the image encoding, and then try to use the model to say which of these class text encodings does it match the closest. And so it'll give you that, it'll say what that class is. Next slide, please. And as code sample, on Hugging Face, you have a very short example, which you can get started with this zero-shot right away. What's happening in this code is you're importing the libraries, you're loading up the model and the preprocessor for the clip model. You're loading up the image. You're generating your text or classes, the text for the classes. So a photo of a cat, a photo of a dog, and so on. And then you're providing the images through the processor. You're running it through the model. You're doing a softmax at the end to get the probabilities. It's very straightforward to create MVPs and prototypes of these zero-shot methods to create something that you can easily demo to somebody. But then as we expand from zero-shot, which is without any examples, to show, you can also use few examples in a method called few-shot learning. So this example, I've borrowed it from Analytics Vidya. Let's go and see how it works. There's an image on the right. And the question is it an armadillo or a pangolin? In your support set, which is the images that you have about the animals, you have 2 images about armadillo, and you have 2 images about a pangolin. So given the image on the right, can you say what that is that an armadillo or a pangolin? So the answer is to let's look at the features that are in the image and the features we have in our images on the left, and try to match with those images, right? For example, let's say it's scaly, cuter. Of course, these are not your embeddings, but just play along with it. So using that, you can say that the image on the right is a pangolin, right? When you're doing actual few-shot learning, you have embeddings, and you are trying to match embeddings of the image on the right with the embeddings of the classes on the left. Next slide, please. Right. And so this problem generalizes into what people call K-way and N-shot learning methods. So for example, K-way is the number of classes, and N-shot is the number of examples that you have in your support set. So let's just quickly understand what the training and support set look like. So the training set is the data that you have available to train your model on. So on the left-hand side, these are all the images that your model is trained on. Your model learns to do it. But during prediction time, what you have is you only have a few examples of a few different classes that you have never seen before. So on the right, you can say there are 4 classes: cat, monkey, lion, and dog. So that becomes a 4-way prediction. And in that support set, you have 1 example for each class. So that is 1 shot. Now, if you had no examples and you were only doing based on the labels, that would be 0 shot, right? But if you have, let's say, 5 examples in your support set, each for cat, each for monkey, and so on, it would be 4-way 5 shot. And so what you do is from the query image, here in case this cute little dog, you get the embedding and you try to match amongst the support set what is the closest animal or class that this matches, and you'll figure out that the probability is highest for the class dog, and then that's your class that you want to say this image belongs to. Next one. And to implement this, here's an example, which is a prototypical network. It's a very easy to understand network, which is why I wanted to present it here. The general idea is you create a prototype of your class by averaging the embeddings of all the images belonging to that class. So in the image on the right, in the plane that you see over here, classes C1, C2, C3 are 3 classes. And the images for those, the embeddings for these images, you are taking a mean and creating these centroids, which are prototypes of these classes. Now you have a candidate image, say X, you get the embedding of that, and using Euclidean distances, you figure out which class is it nearest to, use a nice softmax, and then figure out the probabilities for it. So that's kind of like a very easy way to do this classification. The interesting part about prototypical networks is also the learning that is used to create these embeddings. And the way they use from your small support set is they create a random sample from your support set. They hold out certain data that you can use as query set, and then generate generate the loss function based on this classification. So the model learns to discriminate between the query set and the support set. And so your embeddings become much more amenable towards creating these prototypes. And so that's the embeddings approach to that. Prototype theory has a lot of background in linguistics as well. So in prototype theory, in linguistics, you have the same centroid kind of approaches. But you also have an exemplar theory method, which is similar to a k-nearest neighbor method. So, there's some background in linguistics that you need to consider with prototypical networks. And it does have some limitations. For example, the mean embedding of a pet and a fish is not going to be what a goldfish looks like, right? So these are concepts that are not necessarily translatable with prototypes. And lastly, from the text side with few-shot, Roland mentioned this model, the TARS model. So the same model can also be used for few-shot learning. So you can just a reminder of what that network looks like. On the left, you have your premise, that is the text. You also have the label, and you use the pair itself to feed it to the model and classify it as true if the task that the model is aware to be performed of, it matches that task, or false if it is not. And so, what the paper describes is it can learn from many tasks in a few shot fashion as well. And as one caveat to this is, as it grows or looks at multiple tasks, in this case, it is doing reviews, Yelp reviews, understanding DVpedia, AG News, and so on, topic categorization. So as it goes through multiple classes, there is a slight chance that the model will be forgetting. As you can see, some the accuracies of Amazon, Yelp start decreasing a little bit when you start training it with more data. And so you need to just retrain the models on the same data to make sure that it is learning well. Next slide, please. Great. And
Okay.
I'll hand over to Tobias to speak about weekly supervised learning.
Yeah, thank you. So while in few-shot learning, we use a few labeled examples to describe every class that we want to predict, here we want to take another approach where we use a few heuristics or few rules to describe another, like each of our classes. And I will show you how you can use weekly supervised learning for this. So in the setting that we look at, we have like numerous weak data sources with weekly labeled data. And they have the characteristic that these labels tend to be noisy, so they might be inaccurate, and moreover incomplete. So we not every data source labels every data point that we have. But like the upside of all this is that usually those weakly labeled data sources are cheap to obtain. So here we will look at programmatic rules, but you can also think about using non-expert labelers, so giving your labeling task out to the crowd, or even leveraging other existing machine learning models that might be trained on a slightly different but related task. And then there is like a system that basically consolidates those weakly labeled data sources into one training set, which you can then use with some off-the-shelf machine learning algorithm. And the main task for these algorithms in the middle, like Snorkel or skweak, is to resolve the conflicts that arise in those weakly labeled data sources. But now let's have a look at how we can use a technique called data programming to come up with programmatic rules that can label data points. And the idea is pretty simple. So there are frameworks like this Snorkel that allow you to just write functions in, for example, Python code that take in a data point and spit out like either a class label or like an artificial label that says, I don't know. And with that, you can basically ask each of these functions that you can describe on all your data points, what the function thinks should be the correct label. And with that, you basically get a weakly labeled data source for every labeling function that you come up with. And you can implement them either with hand coding, or you can generalize exemplar data to come up with these labeling functions, or you can leverage existing keyword dictionaries, ontologies, whatever you have. And in some sense, like each of these labeling functions, each of these programmatic rules, they contain more information than just like a class label that you assign to a single data point. And one upside, like on the communication side between the subject matter expert and the data scientist, is that the expert is really forced to explicitly describe the rationale why he thinks a certain data point should fall in a certain class. And if you think about deploying such a system and running this for an extended period of time, having a rule set is way easier to maintain and govern than having like a labeled set of data points, even like, especially if you think about stuff like concept drift. And I want to show you like one example application. If you go to the next slide, thank you, where we were using such a weekly supervised learning approach. We basically wanted to build a smart search system that quickly allows users to filter through like a vast corpus of documents. And the requirement was that each of these users has like a different stance towards like what should be a relevant document to him. And hence, like each user group has its own classifier, and to take away the burden of like labeling lots and lots of data points for each of these user groups, we took this data programming approach where we basically had an interactive and iterative workflow, as you can see on the right here, where we basically sat down with the experts and iterated on this set of labeling functions. So we looked at the existing data, tried to come up with new labeling functions, for example, by looking at data points that are not yet covered by any labeling function, by looking at data points that are misclassified, or by just seeing how we can generalize some exemplar data points. Then we basically tested these labeling functions and modified the rule set and iterated this process in a very interactive way. And by this, we were basically able to quickly bootstrap all of these classifiers without labeling a single data point. And while running the system, like the live system, the production system, we are able to also quickly adapt the classifier in the face of concept drift. And on a psychological note here, what was really pleasing to observe was that the users were trusting the machine learning system more because they could really steer and shape what the machine learning system does by providing these rules to the machine learning system. And to summarize, like this weekly supervised learning approach has some pros and cons, obviously. As I said, like on the pro side, there's the fact that it makes your machine learning system less black box, that there is like a really close interaction between the expert and the machine learning scientist. It's kind of really quick to get something running like a classifier. And in the long run, it's also quite easy to maintain and govern like the set of rules that you come up with. And on the negative side or on the downside, it must be said that like this approach is basically confined to classification tasks because that's where like this naturally works, and mostly to text and tabular data. There are also like extensions to image data, for example, but these seem like rather artificial, I would say. And even if you have a classification problem, not all of these naturally lend themselves to like this approach where you can basically describe your reasoning with a certain set of easy rules. And then when you like create those rules, there's always a trade-off between having like really specific but accurate rules versus having like very broad but inaccurate rules. And it takes some experience to find the right balance here. And what we will probably see in the future is that these weekly supervised learning approaches like integrate well with like active learning type of approaches in frameworks where you can like holistically look at your data and holistically go about labeling or writing rules for your data to train and classify. With this, let's switch gears like a bit and look at another like nifty tool, or a tool that might be nifty in some situations, like the zero label learning. What does it mean? So here, again, we are in the realm of like big modern language models like GPT-3, and the zero label learning is a way to basically distill the knowledge of these big language models into a training set. So what do you do? Or what do you have? Like you have a corpus of data, but you don't have any label. So it's completely unlabeled. But you know, obviously, like the classes that you are looking at. And now you take your big language model and use it to generate training data for some like off-the-shelf, moderately sized deep learning model like the BERT model. And how do you generate this training data? You can like see a sketch of this on the left. You basically give the model in the prompt some examples of your unlabeled data, and then you basically ask it to produce a new data point of a certain class. Like you see, for example, the Yelp rating. So in the context, you give a few examples of how a Yelp rating might look like, independent of any class. And then you ask the model to generate a new data point for a rating of 3 out of 5 stars. And in some situations, this might be really nifty when like these class labels make sense to the language model, and it can then like in the style of your unlabeled data create new data points for you. Yeah, you might come back to this approach if you find yourself in such a situation. And with that, I will hand over to Roland again.
Yeah, thanks, Tobias. Now we'll bring all this together by distillation. As I mentioned before, zero-shot learning models can give you a very quick start, but they are more expensive to run for inference than a regular model. But we can distill the knowledge of a zero-shot learning model to regular model. We have our data set, which is unlabeled, so usually that means it's cheaper to obtain because there's no expert that has to look through the data. We predict in a zero-shot setting the labels for that data set, and then we train a regular classification model on this pseudo-labeled data set. And the result is a much more efficient model. If we train a regular large BERT model, we'll have to do just one pass, regardless of how many labels we have, in contrast to the zero-shot learning model, where we would have to do as many passes as many labels we have. And not only that, sometimes even this distillation results in slightly better performance, especially if we do it with soft labels. So instead of having one for the label that it is, we use the probabilities, and we have the regular model learn the probabilities instead. Distillation can be helpful in many cases, even when just going from big models to smaller ones. Research has showed that going for the largest possible model that you can run is much more efficient, or gives much better results than a smaller model, sometimes 5 or even 10 percentage points. But running those large models in production, when you want to run inference, maybe you want to run it on a mobile device or another latency-constrained environments, is quite difficult, so you would rather have a smaller model. And in this case, you can use the big model as a teacher and the small one as a student, and you can distill the knowledge again. By training the big model on the labeled data set, you make the predictions on the larger unlabeled data set, and then use those predictions to train a smaller model on those, again, the labeled data set plus the pseudo-labeled larger data set. And you can deploy the smaller model. And again, you will obtain a performance that is quite comparable or much better than if you had trained the small label only on the original labeled data set. And you can enjoy the much better latency of the much fewer resource requirements. And in practice, from a project that I worked on, I had about 1,000 labeled documents, 30,000 unlabeled documents. Just as an example, logistic regression gave about 60% accuracy. There were about 30 classes. And if I trained a BERT model, a large BERT model, I would get 75% accuracy. By using the BERT model to predict labels for the other 30,000 documents and then training the logistic regression on the combined data set, I could get logistic regression to perform at 70% accuracy. And logistic regression is simply much faster and much easier to deploy and everything, and runs on CPU really well. So distillation can help a lot. Any questions? Feel free to reach out to us. Here are our email addresses, and looking forward to hearing from you.